You've found Dreamtime Science, part classroom, part lullaby, entirely devoted to satisfying your curiosity while you find your way to sleep. You know, I've been thinking about this curious little experiment called the double-slit, and there's something truly remarkable about how it seems to blur the line between what we see and what actually happens. It's like the tiniest particles are playing a quiet game of hide-and-seek with our eyes, revealing secrets about the nature of reality itself. I can't wait to share why this simple setup has puzzled and amazed scientists for so long. It's a gentle reminder that sometimes just looking can change everything. Your gentle engagement through likes and subscriptions illuminates this quiet corner of knowledge. Let me know in the comments what scientific mysteries you'd love to explore together. Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. There are some nights when the world seems gentler, when the hush of darkness settles over rooftops and tree limbs, and curiosity, like a small flicker, stirs quietly within the mind. It is on such nights that we might find ourselves drawn to mysteries that lie deeper than the surface of things, mysteries that shimmer on the very edge of what we know, as elusive as moonlight on water and as bold as the questions of a child. Tonight, let us set out together upon a gentle voyage, not across continents or oceans, but into the corridors of light itself. Imagine a chamber, dark and silent, save for a single slender beam of light, steady as a heartbeat. This beam, so familiar and yet so strange, is the protagonist of our story. It slips through the darkness, carves its path across a room, and meets a simple obstacle, a barrier, opaque and unremarkable, but for 2 narrow slits cut side by side in its center. This, in all its humble simplicity, is the stage for one of science's most profound and haunting performances, the double-slit experiment. Here, in the interplay of illumination and shadow, the universe reveals a secret that has unsettled and enchanted generations of physicists, philosophers, and dreamers. Let us stand quietly, imagining ourselves in the company of Thomas Young, the English polymath who first performed this experiment in the early 19th century. He was a man of many talents, physician, linguist, and above all, an inquirer into the nature of light. In those days, the debate about whether light was made of particles, as Isaac Newton had championed, or of waves, as Christian Huygens had suggested, was far from settled. Young, with a mind as luminous as the beam he studied, sought a way to peer beneath the surface. He prepared his apparatus, a narrow board with 2 parallel slits, behind which a screen waited in anticipation. He let sunlight, filtered through a pinhole, pass through the slits. And what he observed was not 2 simple bands of brightness, as one might expect if light were like tiny marbles shooting through each opening. No. Upon the screen appeared a pattern of alternating light and dark stripes, as though light itself were weaving a tapestry of brightness and shadow, an interference pattern that whispered of waves overlapping and cancelling each other out. Pause here and consider. Why would 2 slits not simply produce 2 lines? Why would light, so straightforward in its travels, suddenly become an artist, painting a pattern of stripes? The answer lies in the nature of waves. When 2 ripples meet on the surface of a pond, they can add together, crest atop crest, trough atop trough, or they can cancel each other, crest meeting trough, leaving the water calm. So too with light. The crests and troughs of its invisible waves interact, producing regions of brilliance and regions of darkness. The double-slit experiment revealed in all its elegance that light could behave as a wave, not merely as a stream of particles. Yet the story does not end there, for the experiment's true strangeness emerges only as we delve deeper. Imagine repeating Young's experiment, but this time dimming the light until you send photons, single, indivisible packets of light energy, through the slits, one at a time. Each photon, a solitary traveller, faces a choice. Will it pass through the left slit or the right? Surely, with only one photon present, the pattern on the screen should be nothing more than two clusters, mirroring the slits themselves. But as the experiment unfolds, the unexpected occurs. Each photon lands as a single dot on the screen, but as more and more are sent, the dots accumulate, and the familiar interference pattern emerges once again, as if each photon, in its solitary journey, somehow knows about both slits and interferes with itself. It is as though in the quiet darkness, light is both particle and wave, both here and there, both one and many. This is the quantum enigma at the heart of the double-slit experiment. It is a mystery that defies our everyday logic, that hints at a reality stranger than fiction. For if we try to watch, to measure which slit each photon passes through, if we set up an observer to spy on their secret journey, the interference vanishes. The photons behave, suddenly and obediently, like ordinary particles, producing two simple clusters. The act of observation changes the outcome. The universe, it seems, is not indifferent to our gaze. From this gentle, nearly silent experiment, a riddle blooms, a riddle that has wound its way through the halls of scientific thought and into the fertile fields of our imaginations. It is a riddle that has inspired storytellers and dreamers and crept into the narratives of science fiction, bending the rules of reality to conjure visions of time travel, teleportation, and parallel worlds. Consider, if you will, the gleaming corridors of the Starship Enterprise gliding through the cosmos in Star Trek. Here, teleportation, beaming crew members from ship to planet and back again, seems as simple as stepping through a doorway. The shimmer of the transporter, the dematerialization and rematerialization, has echoes of the double-slit experiment's ambiguity, the notion that matter might be disassembled, exist in a state of potential, and reassemble elsewhere. In the world of Doctor Who, the TARDIS slips through time and space with the casual ease of a quantum leap, as if the barriers between moments and places were as thin as the slits in Young's experiment. Yet, these are metaphors, beautiful, beguiling, but not the literal truth. The double-slit experiment does not grant us the power to teleport, to travel through time, or to slide between parallel universes at will. Instead, it offers something subtler and perhaps even more wondrous, a glimpse into the fundamental ambiguity at the heart of the universe. Let us return for a moment to those two slits, standing side by side like gateways to possibility. When we send a photon through, what does it do? Does it choose, in advance, which path to take? Does it split itself, like a ghostly twin, and pass through both at once? Or does it exist in a state of undecided potential, a superposition, until we force it, with our measurement, to declare itself? In the language of quantum mechanics, the photon's journey is described not in terms of certainty, but in terms of probabilities. It is as if, until the very instant it strikes the screen, the photon's path is written in the ink of possibility, not of fact. Only when it is observed, when its arrival is registered, does the universe make a choice. This strange indeterminacy is what makes the double-slit experiment so endlessly fascinating. It is not simply a puzzle to be solved, but an invitation to rethink the nature of reality itself. When science fiction writers borrow its imagery, they are drawn to this central mystery, the sense that the world is richer, deeper, and more unpredictable than we can ever truly grasp. But let us not be swept away by the siren song of fantasy. The double-slit experiment does not allow us to step outside the flow of time, nor does it enable us to vanish and reappear at will. It does not whisper the secrets of faster-than-light travel, nor open the door to alternate universes. Rather, it reveals a universe that is, at its smallest scales, governed by laws that defy our classical intuitions. It tells us that particles can behave as waves, that waves can behave as particles, and that the act of observation is not a passive act, but an intervention, a participation in the unfolding of reality. As you settle deeper into the quiet of the night, let your mind linger on this dance of light and shadow. Picture the patterns forming on the screen, the delicate interplay of brightness and darkness, the silent drama unfolding in the space between slits. Each photon, each ripple of light, is a messenger from the quantum world, a world where certainty gives way to possibility, and where the act of looking changes what is seen. Remember, too, the cultural echoes of this experiment, the ways in which it has seeped into our stories, our dreams, our visions of what might be. In Star Trek, the transporter is not simply a machine, it is a metaphor for the transformation and ambiguity at the heart of quantum mechanics. In Doctor Who, the TARDIS is more than a time machine. It is a symbol of the fluidity and mystery of the universe. These stories do not capture the literal truth, but they remind us that science and imagination are partners in our quest to understand the cosmos. And so, the double-slit experiment stands as both a scientific milestone and a wellspring of wonder. It asks us to question what we know, to peer beyond the surface, to embrace ambiguity and possibility. It is a reminder that the universe is not merely a collection of facts, but a living, breathing mystery, a tapestry woven from light and shadow, certainty and doubt. As you drift, you may find your thoughts returning to that quiet laboratory, to the gentle glow of a single beam of light, to the two slits standing side by side. You may imagine the photons, bold and shy, solitary and communal, tracing their paths across the screen. You may wonder what it means to be both particle and wave, to exist in a state of potential, to be changed by the act of being seen. Outside, the night deepens. The world is quiet, but the questions remain, gentle, persistent, and endlessly inviting. The dance of light and shadow continues, drawing us onward, deeper into the mystery, toward new horizons, waiting just beyond the edge of sleep. And somewhere in the darkness, the next chapter of our journey is already beginning to unfold. The laboratory is quiet, save for the gentle hum of apparatus and the faint tick of an old clock in the corner. The air is thick with anticipation, as if the room itself is holding its breath. In this sanctuary of inquiry, a beam of light is born, a slender, unwavering lance that slices through the darkness, illuminating the dust motes that dance in its path. Light, so familiar and so mysterious, is about to become the protagonist in a tale that will fracture the boundaries of what we thought reality could be. We begin, as so many before us have, with a simple question: what is light? For centuries, philosophers and scientists alike puzzled over this question, each generation peering a little further into nature's secrets. At times, light seemed to behave like a wave, rippling and undulating through space, interfering and diffracting in ways reminiscent of water or sound. At other moments, it acted like a stream of particles, discrete and countable, each photon imparting energy in tidy, indivisible quanta. The double-slit experiment, which we introduced before, sits at the heart of this paradox, offering not only a window into the nature of light, but also into the very fabric of reality itself. Let us step closer to the experiment. Picture a barrier, standing upright like a wall, punctuated by two narrow slits. Behind this barrier, some distance away, is a screen, perhaps a piece of photographic film or a phosphorescent surface eager to record any arrival. When a beam of light is shone toward the slits, we might expect it to pass through and form two bright spots on the screen, as if it were a stream of tiny, luminous marbles. Yet, what unfurls before us is something altogether different and more profound. Instead of two bright bands, the screen blooms with a delicate pattern of alternating light and dark stripes, a display known as an interference pattern. This is the signature of a wave. Here, the crests and troughs from each slit overlap, sometimes reinforcing each other to produce brightness, sometimes cancelling each other out to leave darkness. It is the same dance we might see if we dropped two pebbles into a still pond and watched their ripples merge and mingle. And yet the enigma deepens, for the same experiment can be performed not with a flood of light, but with a single photon at a time. The source is dimmed, attenuated until only one photon is released, like a solitary traveller venturing into the unknown. Each photon, upon its arrival at the screen, leaves a single, pinpoint mark, a tiny declaration of presence. At first these marks seem random, scattered without rhyme or reason. But as more and more photons are sent through, a familiar pattern emerges. The same interference stripes, built up one photon at a time. It is as if each photon, passing through the apparatus alone, has somehow interfered with itself. Here already we stand on the threshold of the quantum world, a domain where logic bows to paradox and the ordinary becomes extraordinary. The question presses upon us, how can a single photon, a discrete particle of light, produce a pattern that requires the interplay of waves? Does the photon split itself, traversing both slits simultaneously, or does it take one path and somehow sense the ghost of the other? To approach this mystery, we must let go, for a moment, of our everyday intuitions. In the quantum realm, the very act of asking, which path did the photon take, becomes fraught with ambiguity. According to the mathematics of quantum mechanics, the photon does not choose a single path. Instead, it exists in a superposition, a delicate, simultaneous combination of all possible paths. Through both slits, the photon's quantum wave function stretches, a mathematical abstraction that encodes the probabilities of its possible fates. It is neither here nor there, but both, and everywhere in between. This notion of superposition is not unique to photons. It is a fundamental feature of all quantum entities, electrons, atoms, even molecules, each capable of existing in a multitude of possible states at once, their futures hovering in a shimmering potentiality. Schrödinger's famous cat, alive and dead in its box, is a poetic distillation of this idea. Until we look, the system remains suspended in a blend of contradictory possibilities. But what does it mean to look? The double-slit experiment invites us to peer closer, to place detectors at the slits and attempt to catch the photon in the act. If we do so, if we set up an apparatus to determine which slit the photon passes through, the interference pattern vanishes. The screen no longer displays its ethereal stripes, but instead records two simple bands, as if the photon had become a mere particle once more. The superposition collapses, and the photon chooses a path, irrevocably, as if the act of measurement has forced nature to make up its mind. This is the collapse of the wave function, a term that carries with it all the gravity of a cosmic event. In the orthodox, or Copenhagen, interpretation of quantum mechanics, the act of measurement is special. It interrupts the quantum dance, projecting the wave of possibilities into a single, definite outcome. Before measurement, the photon is a probability cloud, a whisper of what might be. After measurement, it is a fact. A photon has passed through this slit, not that one. The implications are dizzying. Reality, it seems, is not simply out there, independent and objective. Instead, it is intimately entwined with the act of observation. The universe, at its most fundamental level, is not a cold, clockwork mechanism, but something more elusive and participatory. Our questions shape its answers. Our measurements carve its contours. This interplay between observer and observed is not limited to light. Electrons, too, can be coaxed into the double-slit experiment, and they too will display interference patterns, acting as waves one moment and particles the next. Even buckyballs, complex molecules composed of 60 carbon atoms, have been shown to produce interference, their enormous quantum wave functions unfurling across the apparatus like spectral sails. The quantum world, it appears, is not confined to the microscopic. it stretches upward, threatening to engulf the very fabric of the everyday. And yet, as the scale increases, the quantum strangeness recedes. Large objects do not seem to inhabit superpositions. Cats are either alive or dead, never both. The boundary between the quantum and the classical is blurred, its location uncertain. Some physicists speculate that decoherence, the entanglement of quantum systems with their vast, uncontrollable environments, washes away the delicate superpositions, restoring the familiar solidity of the macroscopic world. Others propose more radical explanations, invoking multiple universes or hidden variables. But let us linger for a while with the superposition itself. What is it like to be in many places at once? Imagine a photon emerging from its source, its destiny unwritten. At the barrier, it meets the two slits, and its wave function splits, parting like a river around an island. On the other side, the two streams recombine, overlapping and interfering, their crests and troughs adding and subtracting in a silent symphony. Where the waves reinforce, the probability of finding the photon is high. Where they cancel, it is low. The pattern is not predetermined, but emerges from the underlying mathematics, a statistical tapestry woven from countless possibilities. But this wave function is not a wave of matter, nor of energy. It is a wave of probability, a mathematical description of uncertainty. The photon has no definite position, no trajectory through space, until it is detected. It is as if reality itself is unformed, a haze of potential, until it is crystallized by an act of measurement. The philosopher's questions return, as insistent as ever. Is the wave function a real, physical thing, or merely a tool for calculating outcomes? Does the universe split into multiple branches, each realizing a different possibility, or does the act of observation select one path from among the many? The answers remain elusive, shimmering on the horizon, always just out of reach. And yet the mathematics works. Predictions are borne out with uncanny precision. The interference pattern, with its alternating bands of light and dark, is a testament to the accuracy and mystery of quantum mechanics. It is a window into a world where certainty is replaced by probability, where particles and waves are not opposites, but facets of a deeper reality. Let us pause and allow ourselves to feel the strangeness. In the world of the very small, the rules we take for granted dissolve. Objects can be in two places at once, can spin both clockwise and counterclockwise, can tunnel through barriers as if by magic. The double-slit experiment is not just a technical curiosity, it is a challenge to our deepest intuitions, a riddle posed by nature itself. It invites us to ask, what is it to be a thing? Is an electron a particle, a wave, or something else entirely? Is the universe deterministic, its future set in stone, or is it a tapestry of probabilities, forever in flux? Can we ever truly know the world, or only the shadows it casts upon our screens? And so, in the stillness of the laboratory, as the photons continue their silent journey, the mysteries accumulate. Each observation answers one question and poses another. Each measurement collapses one possibility and opens up new realms of uncertainty. The wave-particle duality is not a contradiction to be resolved, but a clue, a glimpse into the underlying unity of the cosmos. In the darkness beyond the slits, the interference pattern flickers and grows, a whisper from the quantum world. The photons do not choose between being particles or waves. They are both and neither, and something more. They invite us to expand our imagination, to accept that reality is more complex, more subtle, and more wondrous than we could ever have dreamed. As we stand at the edge of understanding, peering into the quantum abyss, we sense that the answers are there, waiting for us to ask the right questions. The universe, it seems, is a riddle wrapped in mystery, a story that unfolds only as we listen, carefully, to its whispered clues. Yet there is more to this tale, more shadows to chase and paradoxes to ponder. The quantum world is not content to remain hidden. It reaches out touching the macroscopic, hinting at deeper connections. The double-slit experiment, with its elegant simplicity, is but the first act in a drama that spans the universe. For now, we leave the photons to their journey, the interference pattern shimmering on the screen, a record of possibilities both realized and lost. The questions linger, unresolved, echoing through the silence of the laboratory, drawing us ever deeper into the enigma of reality. Beneath the hush of midnight laboratories, beneath glass bell jars and sapphire screens, the double-slit experiment has played out for generations, a slow ballet of light and matter, of questions and the faintest possibilities of answer. Sometimes it unfolds in silence, sometimes with the faint hum of cooling fans and the click of a shutter. But always at its heart is the simple, exquisite puzzle. What changes when we watch? How does the world turn when it knows it is being seen? Let us wander, then, through the story of those who have watched and those who have been watched. The tale begins in the early 19th century, when Thomas Young stood in a darkened room, sunlight filtered through a pinhole, and dared to ask whether light was made of particles or waves. His tools were humble, a card with 2 thin slits, a screen and a patient eye. With his simple apparatus, he revealed a secret, the interference pattern, bands of light and shadow that only waves could make. The world gasped. Light, it seemed, was not a rain of tiny bullets, but a ripple, a trembling surface of possibility. Yet even then there was little to watch but the result, a pattern painted by countless photons, each too small and swift for human sight. For over a century the experiment slumbered in textbooks, a neat demonstration of light's wave nature. But with the birth of quantum mechanics, the double-slit experiment became a crucible for stranger ideas. In the early 20th century, the likes of Max Planck, Niels Bohr, and Albert Einstein began to realize that the division between watcher and watched was not so clean. The world, at its roots, might shift depending on whether it was being scrutinized. The very act of measurement, of posing a question to nature, could shape the answer. To see this, let us peer into the modern laboratory. Here, the tools have grown subtle and precise. Lasers that emit a single photon at a time, electron guns that can hurl subatomic particles one by one, detectors sensitive enough to count the faintest glimmer or thinnest trace. Now, the experiment is not a flood of light, but a careful drip, one photon or one electron at a time, each choosing a path, each writing a point on the screen. Set up the double-slit apparatus. Behind the slits, a detector, perhaps a phosphorescent screen that glows where electrons strike, or a digital sensor that records the arrival of each photon. Fire your particles one by one. At first, nothing seems unusual, a dot here, a dot there, a scatter of points. But as the points accumulate, a pattern emerges, an interference pattern, like the ripples from 2 stones thrown into a pond. Each particle, it seems, has gone through both slits at once, interfering with itself, as if it were both here and there, as if it walked every possible path. But what if you try to watch? What if you place a detector at the slits, determined to know which path each particle takes? Now the story shifts. The interference pattern vanishes, replaced by the pattern you would expect if each particle had chosen one slit or the other. The world, when watched too closely, seems to collapse into certainty. The act of measurement, of observation, has changed the outcome. Here is the heart of quantum strangeness. The experiment's results depend not only on the physical apparatus, but on the information that might, in principle, be available. If you could know which slit the particle passed through, even if you do not look at the data, the interference disappears. If you erase that information or make it impossible to obtain, the interference returns. The universe, it seems, cares not just about what happens, but about what can be known. What does it mean to observe? Is it the eye that counts, or the mind? Or is it simply an interaction, any entanglement, any record, however faint, that leaves a trace? The early quantum physicists wrestled with this question, their debates echoing through smoky lecture halls and late-night letters. Niels Bohr, the great Danish patriarch of quantum theory, argued that the world is not fully real until it is measured. To Bohr, measurement did not require human consciousness, merely an irreversible interaction, a mark left on the world. He spoke of complementarity, the idea that wave and particle are not separate realities, but different faces of the same coin, revealed depending on the question we ask. To ask which path a particle took is to forego knowledge of its interference. To ask about the interference is to let go of which path information. The observer, in Bohr's view, is woven into the fabric of the experiment, not above it. Einstein was less convinced. God does not play dice, he famously protested. For Einstein, reality must exist whether or not it is observed. The moon does not vanish when no one looks at it. He searched for hidden variables, unseen mechanisms that would restore order and certainty to the world. But each new experiment, each clever refinement, seemed to close those doors. Quantum mechanics, for all its strangeness, proved stubbornly accurate. Through the decades, experimenters have devised ever more ingenious ways to probe the dance between the watcher and the watched. Some have used beams of electrons, others atoms or even molecules hundreds of times more massive. Anton Zeilinger, a modern master of quantum optics, has sent buckyballs, soccer ball-shaped molecules of 60 carbon atoms, through slits, watching them interfere with themselves. The boundary between quantum and classical, between the ghostly and the solid, has receded like a mirage. In these experiments, observation is often a matter of entanglement, a delicate web of quantum connections. Place a detector at the slit, and the particle becomes entangled with the measuring device. The universe splits into branches, one where the particle went left, one where it went right, and the interference between branches is lost. If, however, you are clever enough to erase the which path information, to disentangle the branches, the interference reappears as if by magic. Consider the quantum eraser experiment, a gem of modern ingenuity. Here, a photon passes through the double slits, but just beyond, a crystal splits it into two. One photon continues to the detector, the other is sent elsewhere, to a second detector. By measuring the second photon in just the right way, you can choose whether or not to know which path the first photon took, even after it has hit the screen. If the which path information is erased, the interference returns. If it is preserved, the pattern vanishes. The universe, it seems, is not just a tapestry of cause and effect, but a web of potential knowledge. Does this mean that consciousness shapes reality? Some have been tempted by this thought, imagining that the mind of the observer calls the world into being. But most physicists, grounded perhaps by the cold light of the laboratory, prefer a quieter answer. Observation, in the quantum sense, is any interaction that leaves a record, any process that makes possibilities irreversibly real. The mind is not required. An atom, a speck of dust, or a cosmic ray will suffice. Yet the mystery remains. Why does the universe care what can, in principle, be known? The debate between Bohr and Einstein, between the champions of uncertainty and the defenders of reality, has echoed through a century. Bohr, with his quiet certainty, argued that quantum mechanics is complete, that the world's ambiguity is not a sign of ignorance, but a fundamental feature. Einstein, with his restless intellect, searched for hidden patterns, for clues that the dice might not be random after all. Their dialogues, sometimes warm, sometimes sharp, shaped the course of physics. It is easy in retrospect to see them as opposites, but their arguments were more like a duet, each pushing the other to greater clarity. Bohr refined his ideas under Einstein's questioning. Einstein sharpened his doubts in the light of Bohr's answers. Their conversations, recorded in letters and recollections, are a testament to the power of disagreement in science. In the laboratories of the 21st century, the watcher's role has grown ever subtler. Superconducting circuits, cooled to near absolute zero, act as artificial atoms. Trapped ions hover in electromagnetic fields, their states manipulated with lasers. The double-slit experiment, once performed with sunlight and card, is now enacted with single electrons, neutrons, even entire molecules. The questions have grown no less profound. One can imagine the hush in such a lab, as a single particle is launched toward the slits. Perhaps on the far side a detector waits, poised to record its arrival. The laws of quantum mechanics predict only probabilities, a distribution of possible outcomes, a spectrum of might be. When the detector fires, reality crystallizes. This particle arrived here at this moment. The wave function, that strange mathematical ghost, collapses. The act of measurement does not so much reveal a pre-existing fact as create it, pulling one possibility from a sea of maybes. Some physicists, still unsatisfied, have proposed new interpretations. Hugh Everett, in the 1950s, suggested that all possibilities are realized, each in its own branch of a multiverse. In this view, the act of watching does not collapse the wave function, but divides the world, spawning new realities with every observation. The watcher and the watched are both carried along, each following a different thread. The interference disappears, not because possibilities are destroyed, but because they are separated, unable to influence each other. Other thinkers, more cautious, prefer the decoherence story, that the environment itself, teeming with stray photons and jostling atoms, is the ultimate observer. Every interaction entangles the system with its surroundings, washing out interference, leaving behind the appearance of collapse. In this view, the classical world is not separate from the quantum, but emerges from it as ripples emerge from the sea. Yet for all these interpretations, the facts of experiment remain. The double-slit experiment in its myriad forms continues to tease the boundaries of knowledge. Each time a new tool is invented, a sharper detector, a colder trap, a more isolated chamber, the frontier is pushed back. No matter how carefully we watch, the universe seems always to hold one more secret, one more layer of ambiguity. The tools themselves are marvels of ingenuity. Photomultiplier tubes, sensitive enough to catch a single photon. Charge-coupled devices that record the faintest glimmer. Superconducting qubits, their fragile states preserved in crystalline cold. Even the humble slit, once cut by hand in metal foil, is now etched by lasers, narrower than a hair's breadth. Each refinement brings new control, new possibilities, and new questions. Some experiments go further still. Instead of photons or electrons, scientists have used entire atoms, cooled and slowed almost to a standstill, their paths guided by magnetic fields. These atoms, too, show interference, each one a tiny wave, exploring all paths. Even large molecules, thousands of times the mass of a proton, have walked the quantum tightrope, revealing interference patterns. The classical world, solid and certain, is not a separate domain, but a limit. As the systems grow larger and more entangled with their environment, interference fades, replaced by the familiar laws of averages and certainties. But always the role of the watcher remains central. Whether the observer is a human eye, a detector, or the whisper of a photon brushing past, the act of measurement is the pivot on which quantum reality turns. The universe, when watched too closely, becomes definite. When left unmeasured, it spreads into a haze of possibility. Even now, as technology advances, new kinds of experiments are imagined. Delayed choice setups, where the decision to observe or not is made after the particle has passed the slits, entangled pairs sent in opposite directions, their fates linked across distance and time. Each experiment peels back another layer, revealing new mysteries. And so the watchers watch, and the watched respond, in a dance as old as physics itself. The double-slit experiment, in all its forms, remains the stage on which the great questions play out. What is reality? What does it mean to observe? Where does the boundary lie between the possible and the actual, the shadow and the light? In the soft glow of the laboratory, beneath the hum of machines, the questions linger. The watcher's gaze shapes the world, and the watched, in turn, reveal their secrets, one by one, pattern by pattern, in the long, unfolding night. Yet the deeper we gaze, the stranger the answers become. The experiment is not yet finished. The story is not yet told. Ahead, beyond the edge of what we know, the night holds further mysteries, waiting for the gentle touch of observation, for the next act in the unending play of light and shadow. Softly, the world dissolves into midnight blue, and in the hush that follows, your mind slips quietly into the liminal realm where science and philosophy entwine. The question is not merely what nature does when we are not looking, but what it means to look at all. Does the universe know, in some ineffable sense, when it is being watched? The double-slit experiment lingers in your thoughts like a whispered riddle, its patterns echoing far beyond the physics lab into the shadowed corridors of meaning and consciousness. Let us drift, then, into this uncanny region where measurement and mystery embrace. Recall the classic stage, a humble screen, two narrow slits, and a stream of particles, photons, electrons, perhaps even C60 buckyballs flung one by one at the barrier. With no observer marking their passage, each particle seems to traverse every possible path at once, weaving a spectral tapestry of probability. On the detection screen, the pattern that emerges is not two smudges or bands, as one might expect from marbles or bullets, but a delicate array of light and shadow. An interference pattern, the hallmark of waves. Each particle, it seems, interferes with itself, whispering to us in the language of possibility. And yet, when we install a detector, a silent sentinel, to watch the slits and determine which path a particle takes, the pattern collapses. Gone is the wave-like interference. In its place, a simple pair of bands, as if the particle had walked only one road, ignorant of the other. The act of measurement, of observation, rewrites the script of reality. Here, at this strange crossroads, the quantum world yields to our scrutiny, and in doing so seems to change its very nature. What does it mean, then, to observe? In everyday language, to observe is to look, to pay attention, to take notice. However, in the quantum realm, observation is not mere witness. It is intervention, participation, a kind of silent entanglement between the knower and the known. The detector does not simply passively record, it interacts, nudges, disturbs. The quantum state, previously a superposition, a cloud of all possible histories, suddenly crystallizes into one outcome. The wave function collapses, and we are left with a single, solid fact. For decades, this peculiar dependence on observation has unsettled the minds of physicists and philosophers alike. Niels Bohr, the architect of the Copenhagen interpretation, counseled that reality is not merely out there, waiting to be revealed, but is instead co-constructed in the act of measurement. There is no deep reality independent of observation, he suggested, only a world of potentialities, resolved into fact by the act of experiment. Werner Heisenberg, too, spoke of potentia, a realm of the possible from which actual events are plucked by our questions. But what is this observation that holds such power? Is it the conscious gaze of a human mind, the cold click of a Geiger counter, or simply any interaction with the environment that entangles the quantum system with the wider world? Here, the waters grow murky. Some interpretations, such as the many worlds hypothesis, propose that every possible outcome happens, each in its own branching universe, and that observation merely selects which thread of reality we experience. Others, like the relational interpretation, claim that facts are not absolute, but always relative. What is true for one observer may not be true for another. Consider for a moment the act of seeing itself. When you look at a star, ancient photons that have traveled for millennia touch your retina, triggering a cascade of chemical signals that blossom into the sensation of sight. But at that instant, the photon is absorbed, its journey ends, its quantum state collapses. Is it your consciousness, your awareness, that brings about this collapse? Or does it suffice that the photon interacted with a molecule, regardless of whether a mind stands behind the eye? The quantum enigma teases us with the possibility that consciousness and reality are entwined at a fundamental level, yet it always slips from our grasp, refusing simple answers. Think of Erwin Schrödinger and his famous cat, both alive and dead in a box until observed. The thought experiment was meant to lay bare the absurdity of literal wave function collapse applied to macroscopic creatures, yet it also hints at something profound. If the universe is a quantum system, does it require an observer to bring it into being, or does each part of the cosmos participate in a ceaseless web of measurement, with every interaction serving as a kind of observation, collapsing countless superpositions every instant? John Wheeler, a physicist of deep intuition and poetic sensibility, once proposed the participatory universe. In his vision, the cosmos is not a static stage upon which events unfold, but a dynamic interplay of questions and answers, where the act of inquiry shapes the very nature of what is. The universe, he said, is a self-excited circuit, in which observers, ourselves included, play an irreplaceable role. Wheeler's famous delayed choice experiments press this point to the edge of paradox. Whether a photon behaves as a wave or particle can depend on a measurement made after it has already passed through the slits. The future, it seems, can reach back to influence the past, or at least our description of the past bends to accommodate our present questions. In these shadows, the boundary between physics and philosophy blurs. The double-slit experiment, so simple in its apparatus, becomes a window into the deepest mysteries of existence. What is the nature of reality? Is the world fundamentally indeterminate, only fixed when observed? Or is there an underlying order, hidden from view, that we have yet to comprehend? The quantum world, with its superpositions and collapses, seems to invite us to reconsider the ancient riddle. If a tree falls in a forest and no one is there to hear it, does it make a sound? In the quantum forest, the very fall of the tree may be undefined until an ear, biological or mechanical, attends to it. Yet perhaps the greatest mystery is not the nature of the universe itself, but the nature of consciousness that observes it. What is it to be aware, to witness, to know? Is the mind a byproduct of matter, or is it, as some traditions whisper, a fundamental aspect of reality, woven into the fabric of existence? The quantum world does not answer these questions. Instead, it raises them anew, cloaked in the garb of mathematics and experiment. Some physicists, seeking refuge from such heady speculation, adopt the stance of pragmatic agnosticism. What matters, they say, are the predictions, the numbers, the agreement with experiment. Shut up and calculate, goes the refrain. Yet even in calculation, the ghost of the quantum observer lingers. Quantum mechanics does not tell us why measurement works as it does, only that it does. The rules are clear, the meaning elusive. Others are drawn to the edges, experimenting with interpretations that stretch the imagination. The many worlds interpretation, for example, denies the collapse entirely. Instead, every quantum possibility is realized, and the universe endlessly bifurcates into shimmering branches. In one, the particle goes left, in another, right. In this view, observation merely sorts us into one world or another, and all outcomes coexist in an infinite multiverse. But this too raises questions. What is it to be me in such a branching cosmos? Do I split alongside the world, becoming countless versions of myself, each unaware of the others? Alternatively, the pilot wave theory, or de Broglie-Bohm interpretation, restores determinism by positing hidden variables. unseen currents that guide each particle along a definite path, while the wave guides the probabilities behind the scenes. Here, the act of observation does not create reality, but reveals a pre-existing order, veiled by quantum uncertainty. Yet this too comes at a price, introducing non-locality, instantaneous connections across the vastness of space, as if the universe were a single, indivisible whole. And so the quantum mystery endures, undiminished by decades of thought. The double-slit experiment remains a silent oracle, its patterns a script written in the language of possibility and paradox. It suggests that the world is not merely a collection of objects, but a web of relationships in which the observer and the observed are entwined. Each glance, each question, each act of measurement is a thread woven into the fabric of what is real. As you lie in the gentle dark, consider how this mystery seeps into the marrow of everyday life. The device that illuminates your room, the circuits that carry your thoughts across the world, the chemistry of memory and dream, all are governed by these strange quantum laws. The world you inhabit, solid and familiar, is rooted in a realm where certainty dissolves and probability reigns. The atoms in your hand, the photons that brush your cheek, are both particle and wave, both here and not here, awaiting your touch to become real. Perhaps then, the lesson of the double-slit experiment is not merely about electrons and light, but about the nature of questions themselves. To ask is to shape, to know is to participate. The universe, vast and ancient, is not indifferent to our gaze. It responds, in ways subtle and profound, to our curiosity. In this sense, every act of observation is an act of creation, a moment when the possible becomes actual and the world takes form. Yet, what of the deeper questions, the ones that linger long after the last equation is solved? Is there a limit to what we can know? Does the universe hide its secrets behind a veil, or is the veil itself a product of our questions? Are we, as Wheeler proposed, a way for the cosmos to know itself, or are we merely accidental bystanders in a drama far grander than our comprehension? The old philosophers spoke of the world as a mirror, reflectis, nang the mind that contemplates it. In the quantum realm, this metaphor acquires new depth. The act of looking is not passive, but creative. The world is not simply given, but disclosed in the act of inquiry. And as you drift towards sleep, you may find yourself wondering where the boundaries lie, between self and world, between dream and waking, between question and answer. The night is deep, and the quantum riddle persists, humming softly at the edge of thought. Somewhere a particle passes through twin slits, weaving a tapestry of possibility. Somewhere an observer waits, not knowing what the pattern will be, and between them hangs the silent mystery, the mystery of observation, of measurement, of consciousness itself. In this quiet hour, the questions are enough. The patterns linger, shimmering in the darkness, hinting at worlds within worlds, realities within realities. The mysteries of the quantum realm are not puzzles to be solved, but invitations to wonder, to imagine, to dream. And in that dream, the universe watches itself, ever curious, ever unresolved, poised on the razor's edge between the known and the unknowable. So let the questions drift with you into the silence, gentle as the fall of starlight. The story is not finished. The mystery is never truly closed. Somewhere in the hush of midnight, the world waits to be observed, and in that waiting, anything is possible. As our journey through the shimmering veil of the double-slit experiment drifts softly to a close, we find ourselves cradled in the quiet wonder of observation's gentle dance, like a comet tail fading into the hush of space. Rest now in this peaceful mystery, and when your heart is ready, return to Dreamtime Science for more luminous tales that twinkle just beyond the horizon of understanding.